Hello and welcome to another video dedicated to functional groups and reactivity. This is another of a series of videos based on chapter 11 of chemical structure and reactivity and integrated approach. And as a reminder, you have a copy of this chapter scanned and available on Blackboard. I'm going to be talking about reducing agents. I'm going to be talking about the reactivity of aldehydes and ketones, and specifically the reactions of aldehydes and ketones with nitrogen-containing groups, for example, amines. And I will also be looking at the chemistry and the reactivity of acid derivatives, specifically hydrolysis of acid derivatives and some reactions mostly involving acid chlorides. I've divided this topic into several videos, shorter videos, to make it easier to follow. So starting with reducing agents, the two most common reducing agents used in organic synthesis are lithium aluminium hydrate and sodium borohydride. They have a similar mechanism of reaction, but they have slightly different products, and they can be used in different conditions. None of them can be used in acidic solution. They become protonated and they lose their reducing power. Sodium borohydride can tolerate a certain amount of water in the medium. However, lithium aluminium hydride cannot be used in the presence of water. It's too reactive and it reacts quite violently. So the solvent in the reactions with lithium aluminium hydride must always be anhydrous. In this slide, we have an example of sodium borohydride reacting with a ketone. So if you imagine your ketone and the partial positive charge sitting on the carbon of the carbonyl group, and you imagine your sodium borohydride releasing these hydrogen anions, this H minus, the negative charge of the hydrogen can attack the partial positive charge of the carbon in the carbonyl group and displace this double bond of the carbon-oxygen bond. And you end up with this compound, and this is a salt. The reduction has already taken place, and you obtain your product in the form of a salt, a sodium salt. So the last step would be the acid workup, using an acid to remove to break up the salt, to remove all the inorganic parts of the reaction, all the barium salts and the sodium salts, and liberate the alcohol, which is the product of the reaction. This is an example of lithium aluminium hydride reacting with a carboxylic acid. And as you can see, the final product of the reaction is slightly different. We don't reach the alcohol, we stop in an aldehyde. And that is because in a carboxylic acid, we do have something that can act as a leaving group. So it is possible to reform the carbonyl group. So again, if we draw the structure of the carbonyl group, in this case in a carboxylic acid, and if we look a bit at the separation of charges in this molecule, you have the oxygen that have the oxygens that have a partial negative charge. You have the carbon of the carbonyl group with a partial positive charge, and you also have this hydrogen, which is acidic. It is, after all, a carboxylic acid with a partial positive charge. So in this case, the first step is an attack on this hydrogen, which creates this intermediate compound that we have here, creates this salt, aluminium salt of the carboxylic acid. And the next step is another attack by another molecule of lithium aluminium hydride, by another hydrogen anion, this time in the carbonyl group. And this compound is formed. And the difference between now and the previous case is that in the previous case, in the case of the ketone, there was nowhere for this oxygen to go. The only option, there was no possibility of leaving group. That carbonyl group was trapped in between two carbon fragments. In this case, we have this group here that can act as a leaving group, and it actually leaves the molecule. So the double bond of the carbonyl group reforms, and the reduced compound is not an alcohol, it's an aldehyde. So you recover the carbonyl group that was lost halfway through the reaction. Sodium borohydride is less reactive than lithium aluminum hydride, and it will only react with acid chlorides to form alcohols and with aldehydes and ketones, again, to form alcohols. And that's not necessarily a bad thing, because it means that it can be more selective. It means that if you have a structure, an organic structure with several functional groups containing carbonyls, if you use sodium borohydride, you will be able to selectively reduce or acid chlorides or any aldehydes or ketones in your structure. As you can see, lithium aluminum hydride is much more effective. It's a much stronger reducing agent, and it's able to reduce all those carbonyl groups in different functional groups to alcohols or amines if the parent compound, the original reagent contains nitrogen. So now I will ask you to have a go at these two reactions. One is the reduction of this diphenyl compound using sodium borohydride, and the other one is the reduction of this diester with lithium aluminum hydride. You have the answer on page 350 or Killing of Wuthers, but I will encourage you to, using the previous slides that I've shown you, to have a go at yourselves trying to come up with a mechanism for these reactions. And this is all. Thank you for watching, and I hope this was useful.